I do see it.
All right. So shall I kick off, Michael?
Yes, please go ahead.
All right, that's brilliant. So yeah, so after this very interesting session by Jessica about the OCP efforts, what I would like to do now is to show and to share with you all on what happens when you implement these design guidelines for server designs. So Asperitas is a liquid cooling technology vendor and developer. Just to give a bit of an idea what we're talking about in our case with immersion cooling, Asperitas has developed, is working with single phase immersion based on hydrocarbons. And the technology used is passive in nature. It's based on natural convection circulation, which means that the driving force behind the liquid flow is the heat that is being generated by the IT systems themselves. These are placed in the middle part of the tank. The heat that is a driving force behind that flow that's caused by density differences that are applied, which means that a heat will generate a lower density liquid which wants to float, so that liquid moves towards the surface. And on the sides of the IT equipment, we have water-cooled heat exchangers, which are connected directly to the facility, to a facility water circuit. And those heat exchangers provide the cooling in the open bath immersion system. And that cooling creates a lower density liquid again, lower density fluid, which means that the fluid will sink. And that gives us a nice, very organized and predictable natural convection driven circulation mechanism. The technology is developed for high availability platforms, enterprise level deployments, edge systems, but also data centers, and it's completely self-contained and self-sustained. And Asperitas has a very strong focus on optimization for IT equipment, and this is something that we don't do by ourselves. Or just by ourselves. We do that together with a lot of partners. One of these partners, for example, is Shell. They have developed an immersion fluid, which they've launched at the Global Virtual Summit this year. And we are working very closely with them also on material compatibility. Reason why we've been working with Shell is because they're a global supplier and a global manufacturer, and they have the labs to support the material compatibility focus when it comes to immersion optimization of IT equipment. And this is something that will also be included in some other sessions for today. But for now, what I want to focus on is IT equipment optimization. So within Asperitas, we call that the certification process, because that is a process that is very well defined. It's in some areas very elaborate, in other areas very straightforward. And it basically consists out of three main phases. The first phase is a feasibility study, which is started by one of the most fundamental questions. There is, what are the requirements for a platform? So there are several ways of optimizing a platform. Whether you optimize it for density, for performance, or for thermal performance, or thermal capabilities, that may drive you into several different directions. Now, I will be showcasing a couple how that initial requirement influences the design approach. And that first level, that feasibility study, consists of system specifications, thermal designs, and system designs. And that allows you to move into a second phase where you do prototyping, where you start performing material analysis and investigate and optimize for thermal performance. Then a third level is focused on validating that system design and optimizing it, certifying it for thermal use, which means that you're going to be load testing it and you're going to be undergoing a duration test. And after that, a handover back to an OEM or server manufacturer usually occurs. And this whole process is completely focused on everything that has been described in the previously presented design guidelines for immersion cooled IT equipment. This is something that is in the blood of Asperitas. Everything that we work on is also standardized on the OCP open cassette designs. And all these collaborations, all these certification efforts are focused on collaborations with OEMs and system creators alike, with the goal of facilitating fully warranted solutions. Now, just as a quick reminder, at the virtual summit, I also presented the open spec for the Asperitas Open Cassette, and these can be found. And everything I'm going to show you from here onwards is all based on this same spec basis. But before I get into the real examples, again, so we work very closely together with the Liquid Labs, and this is extremely essential. This is relevant for every OEM, every equipment manufacturer out there. As soon as you start looking at immersion and optimizing, or even designing or considering immersion, having alignment with the liquid manufacturers is essential. So we are working with Shell, but 3M is also very active in this field, and also has a lot of knowledge and equipment for the same type of equipment. We're working closely together with Shell because we also work with the Shell liquids, and there is a collaborative approach within all these development projects alike. Now, the three examples I'm going to be giving, I'm going to be showcasing here as realistic examples of actual projects that we are either working on or have completed or have delivered. These are three fundamentally different projects. So one here is an edge platform, which is focused on high cooling temperature tolerance. This is for hotter climates where there is a small, where there's a requirement for a good CPU density, but not the craziest, right? But where the footprint of the entire solution has to be minimized. We're talking about edge locations which may not have sufficient space for large deployments for large systems. The platform here is focused on AMD, and it's focused on data processing. The second example is an enterprise mainstream platform, which is based on a 2U system, and we've implemented that in a 21-inch environment, or in a 21-inch open cassette, while the original system is 19-inch. This platform is focused on high availability as the highest priority, with high overall efficiency, but also with high serviceability requirements. And finally, there is an HPC platform, which is a high performance implementation, an HPC implementation based on CPU and GPU densities and high overall efficiency. And this platform that's being used is based on Intel NVIDIA, and the application is focused on AI and machine learning. So these are three different projects that I'll be showing, and I will elaborate on the differences between these type of design engagements. So the first platform for the edge data processing, that is based on a Supermicro platform. And with the high temperature tolerance focus, there has to be additional attention to the thermal design of the entire system, which means that there are also limitations for which components can be used in an environment. And when I state 48 degrees C, we are now already with the same platform at the levels of 50, 51 degrees C cooling. We call this a medium CPU density focus. There's still a lot of CPUs. So if we're looking at the space that we're actually utilizing, the density is pretty high, but we're not talking about the highest TDP specs in this case. But the CPU selection has actually occurred based on the thermal properties, thermal capabilities of the CPUs. And the minimized footprints also has a consequence. That means that the board layout and the positioning has to be redesigned. This platform is implemented, this 19-inch server is actually implemented in a 15-inch wide design, simply to allow for maximum utilization of floor space. And not just floor space, but also three-dimensional space. Now, the type of things I've included some examples here of how we've dealt with that, because if we're looking at a 15-inch chassis, it's not actually possible to fit the two specific boards that we need to use next to each other in the same base plate. So in this case, one of the boards is oriented upside down. Now, when I say upside down, there is this thing with immersion where chassis are not positioned in a horizontal position anymore. We're talking about vertical implementation, which means that there is no such thing as upside down. They're all straight up, right? So you have some additional design liberties when it comes to solving these type of challenges. So this system has been optimized for high liquid flow abilities. The main thermal sources for the flow in this case are the CPUs, and these are 180-watt CPUs. And there is a power supply, which is an 80+ PSU, which should be efficient about 94%, but we're calculating that with 10% losses. Because when we design for optimization, we want to ensure that we have a certain headway, a certain headroom when it comes to actual deployment. Instead of having serviceable sleds, which require some space and some freedom, require physical space to be usable, we've chosen to physically mount the boards inside the chassis. So that means that the failure domain right now is 2 nodes in the chassis with a single power supply. The CPUs are placed as low as possible in the liquid. Because of the thermal optimization challenge, we need to have all the hottest components as deep into the liquid as possible. Which means that everything is focused on achieving every possible millimeter that we can, because every millimeter may add a degree Celsius in cooling tolerances. In this specific case as well, when we're talking about heatsink design and CPU heat rejection, we're actually utilizing the flow rate, the combined flow rate of both heatsinks positioned beyond each other, positioned in each other's shadow, because that shadowing effect will actually increases the flow rate that can be achieved, which in return, again, affects the thermal performance of the CPUs themselves. So there is some creativity that can be applied when dealing with immersion cooling. And after this design phase, when you're looking at implementation or the test phase, one of the very first things that needs to be looked at and addressed is material compatibility. So in our case, how we do this is first by opening the box and just making pictures, documenting every little aspect about the system, so we have something to compare with after we've run initial immersion tests. We identify capacitors, thermal compounds, labels, fan locations, which the system may depend on for fan simulator applications. Nowadays, luckily, we don't run into a lot of those anymore. Most systems are compatible with fanless operation, but still something to look out for, especially within power supplies. One of the things that needs to be checked upon is material data sheets. And here's the thing when it comes to IT equipment, it can be very difficult to find material sheets for components used in an in a set of IT equipment. So very often we rely on thermal bath testing and photographic evidence, visual confirmations that certain materials have not reacted with the liquid. But testing is also key. So one of the examples that we do with the system is 100 times rapid power switching to weed out any potential issues with PSU relays. For more details on specifics, I refer to the white paper that was just presented as well. And of course, there's some duration testing that needs to be done. I'm just going to skip over a slide here. One of the things that you want to be looking at as well when it comes to the testing phase is how the system operates under load. So here you see some of the tracks, some of the data logs of a platform validation. This is a fully populated system where you can see the thermal parameters of that system and how we look at, for example, CPU performance. How does a CPU perform thermally? In this case, on the top left side, we discovered temperature hysteresis, and due to some thermal effects around the heatsink. When you start heating up the vapor chamber with hot liquid, it actually may have an effect on the overall performance of that heatsink. Which leads me also to the important part, which is also heatsink optimization. One of the most fundamental advantages that can be achieved with immersion cooling is actually in something as simple as heatsink design. If you look at an average heatsink, which is designed for air, you're just looking at a very close positioning of fins, narrow spacing between the fins, and the fin thickness is usually also not that big, and that's all designed to force air through a lot of surface area. But if you look at immersion with the viscosity of liquid, that same heatsink design, you might as well consider it a solid block, because liquid doesn't move through those small spaces as easily as air does. And just with a slight optimization in CPU selection, or sorry, in heatsink selection, in this case, this is a small optimization in the fin pitch, a minor optimization in fin thickness, and a really, almost no optimization when it comes to heatsink shape. But we're already seeing an increase in CPU performance. So the blue dotted line in these graphs, they're at the same scale, shows the clock speed of a testing process that takes place on that same CPU in the exact same conditions with two different heat sinks. Right, so you see an immediate increase in efficiency of that heatsink. So that just shows the effect of looking at optimization on the heatsink and how valuable that can be. Now, the second platform that we're looking at is an enterprise mainstream platform. Now, the biggest difference with the previous one is that this one is not focused on maximizing thermal tolerances, thermal capabilities, but at delivering high availability and high value to host high value platforms which need to be serviceable. And this is focused on overall efficiency and high serviceability. As in, we need to be able to service nodes. Well, here comes one of the first challenges. When you are looking at serviceability and immersion, as has been mentioned a few times now in this presentation lineup, there is only one side of the system that is accessible. Now, if you look back at the original system, one side of this platform is equipped with hard drives, and the other side is equipped with plates. Now, if you're going to put this in vertically in an immersion tank, one of these sides will not be accessible for hot servicing. So you have to make a choice which side is more relevant for servicing. In this case, for this particular platform, the choice is made for the compute nodes, for the blades. So the decision was made to remove the drive base and to extend the blade designs for lowered positioning into the chassis, into the system. The original backplane designs have been repositioned towards the lower end of the system, and the off-the-shelf blades are actually still supported. So the blades themselves are unmodified in this platform. Material compatibility focus, again, this is the first thing that happens with every system that comes in. is focused on capacitors, thermal compounds, labels, fan simulator applications, you name it. And the test methods are, in this case, for this platform, well, not that difficult because we were already familiar with most of the equipment used in this platform. So all components are known or pre-certified, but we still apply visual checks and we still document these kind of systems for material compatibility studies. And of course, we do the duration testing. Now, when we looking at thermal optimization for reliability, the results of this platform is focused on the lower placement inside the liquid of the plates to gain access to the lowest temperature, the lowest temperatures in the tank. In this case, not so much focused on reaching the highest possible cooling temperatures, but implementing the safest environment for that CPU to be in. Thermal shadowing in this case is equalized with different heat sinks, similar to the original design. And the power supplies are located in this case in the same thermal layer as the power supply. So all the critical components are equally cooled, are supplied with the same temperature fluid. And this system is now hot swappable, fully serviceable from the liquid service. And all the ports are extended for dry cable management. Right, so we're using port extenders both for the high performance network and for the network interfaces, for the Ethernet interfaces, but also for the power cables. Right, so if you look at power supply, how that's positioned, the power interface is actually redirected all the way to above the liquid surface, so that everything is dry serviceable. And the test approach for all these platforms is always focused on maximum population of the system, maximum equipment, maximized population of memory, maximized CPUs, because this is focused on an industry availability, not a specific customer or one specific platform, but for a general use, enterprise platform. And this is what some of these tests looks like. So what you're seeing here in these tests is with specific cooling inlet temperatures. This is one of the overheating tests that we do on purpose. So this has to be part of that test process where you're going to be investigated. Okay, so what really is that throttling temperature? If I have this assembly, this optimized system, what do I need to do? What kind of temperatures do I need to feed it before it starts impacting the performance of this platform, right? The actual cooling temperatures I'm not sharing in these slides, but here is a potential outcome of such an exercise, right? Where you look at the density of a chassis versus the cooling requirements for different types of service specs and for different types of energy densities in a chassis. What does it do with the tolerance for the entire platform? Now, finally, just to finish this off, an example of an HPC environment. This is focused on high performance computing and high chip densities. We're talking about 4 heavy duty GPUs and 2 pretty high-end CPUs, combination of Intel and NVIDIA. And we're looking here at the optimization capabilities. And one of the things that is interesting to note here is that we've integrated a power supply in the system, which was originally designed for busbar operation. That actually has a density effect because it saves us about 17% space of the tank because we don't need the power shelf. And we've been able to convert 1 OU into 1 U. Now, this might sound odd in an OCP domain, but due to the space savings in a tank, this is actually relevant because in a tank, we're working with a horizontal space. Every rack unit translates into square meter surface area that is required. So we can't stack vertical in that sense. We can stack densities, right? And because we don't need airflow features, we don't need fans, all that space is now freed up for an optimized component placement. Right, so when we're looking at thermal shadowing, the most important considerations here are to avoid thermal shadowing. So all the GPUs are on parallel, and this is similar to the original Air design. And the CPUs are placed as low as possible, as long as the main board allows it. Right. The InfiniBand network adapters, one of the considerations for placement of that is the fact that they're more temperature tolerant. So they can be placed in the higher temperature layers, and ports are all extended for service access, for dry access. Now there's a couple more platforms that we have built and that we've developed, all related to the OCP domain. We're working on the Olympus platform, we're working on other compute platforms. And these are all focused on high density computing and optimization of IT equipment for immersion. So one of the lessons learned around this is the fact that improved system capabilities are definitely unlocked by platform optimization. We've been able to create a data processing platform that now operates at around 50 degrees Celsius cooling, and actually delivering 60 degrees Celsius as a waste product, right? So a water stream with that 60 degrees Celsius is relevant in many areas in the world. And differentiation between workloads allows optimization for desired goals. So optimizing something for thermal or high density or high availability actually results in different platform approaches, different design approaches. And through the material compatibility studies, we can make these platforms incredibly predictable, right? Especially in combination with the natural convection flow, which is very predictable in nature. But we're also able to prove that with the tests at scale, which also allow for the identification of further optimization steps. Now, all these optimizations can only be made possible by a collaborative approach, right? So the solution, the immersion solution, does not dictate which, or does not determine which optimizations can be achieved. That is actually dictated by the collaborations that are put in place to make it possible, right? So we are not a liquid lab, but we have a partner that does it, that does have that, that's Shell. And we are not an IT equipment manufacturer, but the OEMs around us, they are. We are not a chip manufacturers, but Intel and AMD and NVIDIA are. So it's important to work in close collaboration with all the parties, especially here in OCP, and this is also the value of OCP here, and also goes into the call to action. It is very, we're going to be very happy if more people, more vendors, more manufacturers start joining and contributing immersion related content in the immersion server and ACF groups. And we do need that collaboration to allow further optimization of IT platforms for immersion, because that will unlock the new, a larger potential for IT equipment, but also for sustainability. And for that to really work out, we need to start cross-pollination within OCP to build that effective ecosystem. And OCP does build that effective ecosystem. And the sharing of knowledge is something that a lot of companies in the industry are still hesitant about, but it does help increase the immersion potential, and not just the immersion potential, but also the IT equipment potential. So with that, I would like to conclude. For more information on this, you can always contact me and join the immersion group as well. If there's any questions, I think we have to be quick because we're moving over to Jamil Shah and Eduardo Azevedo. Are there any questions? Okay.
All right. Thank you, Rolf.